And so we've learned that the change enthalpy of a reaction can be calculated using standard enthalpies of formation by doing products minus reactants, or it can be calculated using Hess's law, where you add a series of reactions, you add the corresponding change in enthalpies, and then sum of the corresponding change in enthalpy is equal to the change enthalpy for the net reaction. The change in enthalpy is actually equal to heat transfer to the system, assuming only expansion work and constant pressure. In this video, we'll talk about different types of enthalpies and how they're related to intermolecular forces. And so different types of enthalpies, like enthalpy of vaporization, enthalpy of fusion, can be used to calculate how much heat a system absorbs or emitted. These different types of enthalpies can be directly related to intermolecular forces. And so different types of enthalpies, intermolecular forces, very important. What you should be able to do after watching this video is describe how different types of enthalpies are to just change in enthalpy for specific processes. Given a process, you should be able to determine the change in enthalpy of that process using tables of different types of enthalpies. Put a series of compounds in order of increasing enthalpy of vaporization or enthalpy of fusion based on intermolecular forces. You should be able to put a series of ionic solids in order of increasing lattice enthalpies and in order of increasing melting points based on a strength of the ion-ion interaction, which is classified as an intermolecular force. And so here's a table of different different enthalpies. Delta HR is the standard. It just means enthalpy of a reaction. Delta HF is enthalpy of formation. Elements in a standard state going to 1 mole of product of interest. Enthalpy of vaporization is delta H vap, and so going from liquid to gas. Delta H FUS is enthalpy of fusion, solid to a liquid. Delta HC is enthalpy of combustion, so that's combustion of 1 mole of a compound and oxygen, O2. Delta HL is lattice enthalpy, that's going from ionic solid to gaseous ions. Delta HYD, enthalpy of hydration, gaseous ions to solution. Enthalpy SOL is enthalpy of solution, so solvent plus solid going to solution. Delta HB is bond enthalpy, molecule to fragments. And so for all these, you should be able to identify the different type of enthalpy, the physical process that they represent. And you should also be able to know if they're always positive, always negative, or can be either. And so enthalpy of formation we've talked about before is elements in a standard state going to 1 mole of the compound of interest. They're important because we cannot determine enthalpy in absolute term, and so we define enthalpies relative to elements in their standard state. And so if we need the enthalpy for a compound, we have to take elements in a standard state and form 1 mole of the compound and measure the change in heat, constant pressure, and assuming no expansion work. Again, enthalpies elements in their standard state are defined as having 0 enthalpies. And so here's a table of enthalpies of formation. Again, elements in their standard state, 0 enthalpy. And all these are measured relative to elements in their standard state. Notice the enthalpies of formation can be positive or negative. And so if we want to calculate the change enthalpy for a reaction, we use the enthalpies of formation that are defined relative to elements in their standard state. And so here we have H2O liquid going to H2O gas. And so we take the gas enthalpy minus the liquid enthalpy. Again, products minus reactants. The capital sigma means sum. And so we sum up all the products, sum up all the reactants. And so using the table, we see that we have minus 242 minus 286 gives us a positive 44 kilojoules. Now, it seems like this would be the enthalpy of vaporization for water. But, again, the enthalpies of formation, you notice that you have that little superscript 0 means standard conditions, which is 25 degrees Celsius. And so calculating enthalpy of vaporization this way will give you a slightly different answer because, again, enthalpies are defined at 25 degrees Celsius. Enthalpies of vaporization are actually defined at the boiling point. And so if you calculate enthalpy of vaporization this way, you compare it with the table of enthalpies of vaporization, you should see that there's a slightly different difference. Enthalpies are temperature dependent, even though often we'll assume that they're temperature independent or their temperature dependence is negligible. And so enthalpies of vaporization change enthalpy going from a liquid to a gas. And so gases always have higher enthalpy than corresponding liquid, which always has a higher enthalpy than corresponding solid. And so going from a liquid to a gas, we're going to higher enthalpy, and so enthalpies of vaporization are always positive. Now here's the table of enthalpies of vaporization at boiling point. And so intermolecular forces affect both enthalpies of vaporization and boiling point. Think about enthalpies of vaporization, the amount of heat that has to be added to overcome the intermolecular forces. And so the stronger intermolecular forces, more heat has to be added, and so larger the enthalpy of vaporization. You can also think about in terms of a competition between kinetic energy and intermolecular forces. The stronger intermolecular forces, the higher the kinetic energy the particles need to overcome those intermolecular forces. And so the stronger intermolecular forces, the higher the boiling point. And so stronger intermolecular forces, higher enthalpy of vaporization. Stronger intermolecular forces, higher the boiling point. And so if we look at this table, the ones in red only have London dispersion intermolecular forces, and so that's the weakest intermolecular forces, and so notice that they have low boiling points and small enthalpies of vaporization. The ones in blue have hydrogen bonding and London dispersion. Hydrogen bonding is the strongest intermolecular forces between molecules. Ion is obviously stronger, but hydrogen bonding leads to a higher boiling point, a higher enthalpy of vaporization. Helium is the element with the lowest boiling point of 4.2, enthalpy of vaporization in 0.084, very small. You look at water, it's got a boiling point of 373, much higher, and enthalpy of vaporization of 40.7. And so again, enthalpy of vaporization is heat required to cause 1 mole of liquid to go into the gas phase. Enthalpy of fusion is the heat required to cause 1 mole of a solid to go into the liquid phase. And so again, because enthalpy of the gas is greater than enthalpy of liquid is greater than enthalpy of solid, you would expect that enthalpies of fusion are always going to be positive. And again, here we see a table of enthalpies of fusion and the melting point. And so enthalpy of fusion, heat required to convert a solid to a liquid. And so you have to partially overcome some of those intermolecular forces. And so the stronger intermolecular force, the higher the enthalpy of fusion. Again, that's what we see. The ones in red have only London dispersion. The ones in blue have hydrogen bonding plus London dispersion. And so again, poor helium has enthalpy of fusion of 0.021. We can think about melting also in terms of competition between intermolecular forces and kinetic energy. And so the weaker the intermolecular forces, the lower the kinetic energy needed, the lower the melting point. Temperature is just a measure of kinetic energy at the atomic level. The stronger intermolecular forces, so like ammonia or water, the higher the kinetic energy the particles need to overcome the intermolecular forces, and so the higher the melting point. And so strong intermolecular forces lead to a higher enthalpy of fusion and also higher melting point. And so enthalpy of gas, it's important to remember enthalpy of a gas is always greater than the corresponding enthalpy of the liquid, which is always greater than the enthalpy of the corresponding solid. And so to go to the right is always endothermic. Heat always has to be a reactant. Delta H is always positive. To go to the left, it's always exothermic. Heat is always a product. Delta H is less than 0. And so enthalpies of fusion is the amount of heat required to convert 1 mole of a solid to a liquid. It is always positive. Enthalpies of vaporization is the amount of heat required to convert 1 mole of liquid to a gas. It is always positive. And again, enthalpy of fusion defined at the melting point. Enthalpy of vaporization defined at the boiling point. If you try to do products mass reactants using the standard enthalpies of formation, again, the number will be slightly different because standard enthalpies of formation are defined at 25 degrees Celsius. And so if we look at the reaction below, we notice that we have O2 as a reactant, we have CO2 and water as products, and so that actually looks like a combustion. And so we can calculate the delta H for that reaction by doing products minus reactants. You should remember that you have to include the coefficient. So notice that water has 2 times it. And so when we're calculating products minus reactants, we have 2 times enthalpy of formation for the water. Notice that we have 3.5 times enthalpy formation of the O2. And so we get a delta H of minus 727. And so remember, elements in standard state have enthalpies of formation of 0. Oxygen is an element in standard state, and so its enthalpy of formation is 0. And so this is a combustion reaction. And so the change in enthalpy for the reaction is the enthalpy of combustion. Now what we burned was CH3OH, which is methanol, and so the enthalpy of combustion of methanol is minus 727. And so enthalpy of combustion is the amount of heat transferred from the system to surroundings when 1 mole of the compound is burned in O2, producing CO2. You should remember, if you don't have enough oxygen, you produce CO, and so we're always saying there's enough oxygen to produce CO2. Now, if you're burning something that contains hydrogen, you'll produce water. If you're burning something that contains carbon and you have enough oxygen, you should produce CO2. Here's a table of combustion enthalpies. And again, because something's being burned and you're transferring heat from the system to the surroundings, enthalpies of combustion are always negative. Lattice enthalpy is the energy required to convert ionic solid into gaseous ions. And so, for instance, you can imagine sodium chloride going to sodium ions gaseous phase plus chloride ions gaseous phase. Now, the importance of the lattice enthalpy is actually it's a measure of the strength of the ion-ion interaction in an ionic solid. And so ions in the gas phase assume, typically for gases, we assume the intermolecular forces are negligible, that there's a lot of space between the particles. And so the only difference between the ions in the gas phase and ions in the solid phase is the ion interaction of the ionic solid. And so lattice enthalpy is a measure of the strength of the ion-ion interaction. Now, because we're going from a very stable state to a very unstable state, we're going to have to put a lot of heat into the system. And so lattice enthalpies are always positive. And so below we can see a table of lattice enthalpies. And so the stronger the ion-ion interaction, the larger the lattice enthalpy. Actually, we can use this little flow diagram. The larger the charges on the ions, the stronger the ion-ion interaction, the larger the lattice enthalpy, also the higher the melting point. The smaller the ions, the closer ions, the stronger the ion-ion interaction, the larger the lattice enthalpy, the higher the melting point. But you have to remember that the charge is the most important consideration. And so you always put the compounds in order of charges, and then you do it in terms of ionic sizes. And so if we look at this table, we'll notice that down at the bottom we have magnesium oxide, which is composed, and calcium oxide composed of +2 and -2 ions. They have lattice enthalpies of greater than 3,000. The magnesium fluoride, a +2 and a -1, has lattice enthalpies in the high 2,000. And then lithium fluoride, for example, has lattice enthalpies of about 1,000. And so it's really kind of cool, just based on the charges of the ions, we can put them in order of increasing lattice enthalpy. The bigger the charges, the larger lattice enthalpy. If you're looking at compounds with the same charge, you go by size. So for instance, lithium fluoride lithium is smaller than sodium, and so lithium fluoride has a higher lattice enthalpy than the sodium fluoride. But also melting point should also follow this trend. The stronger the ion-ion interaction, the higher the melting point. And again, we can just use the charge on the ions and the size of the ions. Enthalpy hydration is the change in enthalpy when the gaseous ions are dissolved in water. And so you can imagine chloride gas ion going to aqueous chloride ion. And so you're going from something less stable to something more stable. And so your enthalpies of hydration are always going to be negative. Now we can actually add enthalpies. So if we add the chloride ion going to the chloride aqueous, sodium gaseous ion going to the sodium aqueous ion, we get those combination and we add the corresponding delta H's. And so again, remember Hess's law that if you add reactions, you can add the corresponding delta H's. And so enthalpies of hydration, again, are always negative. The stronger the ion-dipole interaction between the ion and the water molecule, the more negative. And again, we can think about it in terms of charge and then size. And so you notice that the +2 ions have more negative enthalpies of hydration than the +1 ions. Again, charge is most important. And then if we look at the size, notice that lithium is smaller than sodium, which is smaller than potassium. And so lithium is more negative enthalpy of hydration than sodium, which is more negative than potassium. And so one question you should be able to do is put the following order of decreasing enthalpies of hydration, which means more negative. And so we see aluminum +3, and so biggest charge, we should assume that's going to be the most negative. And now we have the magnesium +2, and well, let's put it in charges first. So the +3 is going to be the most negative. The +1 and -1 will be the least negative. Now we do it in terms of size. Hydrogen, helium, lithium. Let's think about a periodic table. And so I think calcium is below the magnesium. And so magnesium is going to be more negative than calcium. Lithium is above chlorine on the periodic table. And so lithium is going to be more negative than chlorine. And so again, we do it in terms of charges first, and then in terms of physical size. We treat a +1 and -1 the same. We treat +2 and -2 the same. And so again, enthalpies of hydration, they follow the same trend as the ion-ion, charge first and then size. Enthalpies of solution is the change in enthalpy when something dissolves in something else. And so you can imagine going from a solvent plus a solute going to the solution. Now the way of thinking about it is that in the solvent you have the solvent-solvent interactions, in the solute you have the solute-solute interactions, and in the solution you're going to replace some of those interactions with solute-solvent interactions. And so things only dissolve when the relative strengths of the interactions are similar. And that's why we get likes dissolve likes, because if the intermolecular forces are similar, it means the interactions should be similar.
We can imagine the process of mixing two liquids as occurring in 3 steps. First, the intermolecular forces of one liquid are overcome. We can then think of the liquid as being converted to a gas in an endothermic process. Next, the same thing occurs to the second liquid. Finally, these two gases condense together, releasing energy. The energetics of the overall process depend on the relative strengths of the intermolecular forces involved.
And so typically for mixing, the most important thing is entropy. But if the change in enthalpy is too large, it will not mix. And so things will mix even if the enthalpy of solution is positive or negative. But again, if the change in enthalpy is too large, then you will not get the mixing. And so you can imagine enthalpy of solution of ionic solid into aqueous ions. And so the reason ionic solids dissolve in water is because the strength of the ion dipole interaction is fairly strong. Now we can actually calculate the enthalpy of solution ionic solid dissolving in aqueous ions. And so we have sodium chloride going to sodium ions gaseous phase plus chloride ions gaseous phase. And so that's the lattice enthalpy for sodium chloride of 787. And then we have the enthalpies of hydration for the chloride ion and the sodium ion, which is combined of minus 784. And then if you add those two reactions, you have the changes in enthalpy. And so you get enthalpy of solution of 3 kilojoules per mole. It's really kind of interesting that the final change in enthalpy is so small, considering the magnitude of the lattice enthalpy and the enthalpies of hydration.
The dissolution of potassium fluoride can be thought of in 2 steps, although the reaction does not really occur this way. First, we imagine the potassium and fluoride ions separating. This is an endothermic process. Then the ions are hydrated. This is an exothermic process. The combination of these two energies is the enthalpy of solution.
And so again, enthalpy of solution can be a +2 or -2. Those are close enough that you should be fairly soluble. But if the enthalpy of solution is too positive, then it will not dissolve. And so again, this is the process of dissolving potassium fluoride into water. And so we get a minus 18 kilojoules of heat. And so that's going to be, should readily dissolve. And again, it's also kind of cool. It's about intermolecular forces. Again, remember the last enthalpy, the top reaction is from the ion-ion interaction. It's a measure of the ion-ion interaction. And then below that, we have the hydration enthalpies, which is a measure of the ion dipole interaction between the ion and the polar water molecule. And also, please remember that when something is dissolved, solute-solute and solvent-solvent interactions are replaced by solute-solvent interactions, and that's where likes dissolve likes come from. We can look at solubility as a function of temperature. When delta H of solution is positive, the solubility is greater at higher temperatures. We can also talk about supersaturated solutions, and so those are solutions that have more stuff dissolved than is thermodynamically stable, and so they can quickly crystallize when they have a C crystal or when there's the vibration of the little metal thing.
A solution of sodium acetate in water is in a flask. A few small crystals of sodium acetate are placed on the top of the laboratory bench. The solution from the flask is poured over the crystals. As the solution contacts the crystals, its color changes from clear to white very rapidly, and it crystallizes into a solid mound of material that builds up into a fairly tall vertical structure. The probe from a digital thermometer touches the solid sodium acetate to test the temperature. It is seen that the material is quite warm. The process of crystallization is an exothermic process in which heat is given off to the surroundings.
And so sodium acetate has an endothermic enthalpy of solution, meaning it has a positive enthalpy of solution. Now the video shows you the reverse process, going from the sodium ions, acid ions, into solid sodium acetate. And so the reverse process is going to be exothermic.
Now a commercial application of this crystallization process is shown. A metal disc is manipulated inside a sealed plastic bag holding the sodium acetate solution. This causes the sodium acetate to crystallize. The digital thermometer shows that the temperature of the heating pack has gone up significantly from room temperature.
So a nice
This
application
heating pack
of
provides
enthalpy
an
as
easy,
solution.
portable method of having heat available whenever and wherever it is needed.
And so some commercial heat packs are actually made of supersaturated solutions of sodium acetate. Now, gases dissolved in a solvent are exothermic, hence they're more soluble to lower the temperature. And so again, we're talking about an enthalpy of solution. We're going from gases to dissolved gases, aqueous. Now, if we think about it, gases, again, we assume intermolecular forces are negligible. And then when you dissolve in water, you have a London dispersion. And so the gas molecules are typically nonpolar. And so actually it'll be dipole-induced dipole interaction between the nonpolar molecule and the polar water.
When a can of soft drink is opened, a whooshing sound is heard, and the solution begins to release bubbles. The escaping gas is carbon dioxide. Henry's law explains why the gas leaves the liquid only after the can is opened.
And so the gases dissolving liquid is an example of enthalpy of solution. The inside the can, I think, is something like 5 atmospheres of CO2 that pushes the gas into the liquid. And then when you open the can, you're releasing some of that CO2, and then CO2 also starts leaving the liquid because it's an equilibrium process. We can actually describe the solubility of the gas in the liquid using Henry's law. And so the solubility of the gas in the liquid is equal to a constant Kh times the partial pressure of the gas. And so the higher the partial pressure, the more soluble the gas is in the liquid. But which gases are more soluble in liquids depends on intermolecular forces, which is determined by or measured by the enthalpy of solution of the gases in the liquid. And here's some Henry law constants. And again, you'd expect helium to have a very weak interaction with the water molecules. And so it has a very small constant. And so helium is not very soluble. Nitrogen and oxygen are a little bit bigger. And so they're going to have a stronger induced dipole-dipole interaction. And so a larger Henry's law constant. So they're more soluble in the liquid. And so we can describe it using enthalpies of solution, and again, they're related to intermolecular forces.